Hi folks. So last time we were talking through mechatronic design. We were thinking about what is mechatronics. I used that Venn diagram with the overlapping circles to think about mechatronics as being an overlap region between the different domains. And so now we want to dive into the first domain, which is going to be electronic systems. Now, you all have taken a course on circuits and electronics in the past, so hopefully this is all just review for you, and you'll probably be sort of bored and skipping ahead, and that's fine. This should be entirely review because it's stuff you've seen before. But let's go ahead and remind ourselves about electronic systems. So first question is always, why does this matter? Why does this matter in terms of your project for the semester? Why does this matter in terms of mechatronics? Why does this matter in terms of your life? So at this point we would normally do a discussion, but obviously we're not doing discussion because we're all remote right now. But pause the video, think about it for yourself briefly. Why does electronic systems matter to you in terms of mechatronics? So the things that I thought of were that we are going to have some sort of sensor and some sort of actuator in order to make our mechatronic systems work. And there's going to be some sort of microcontroller providing the brain where we're going to put our finite state machines when we get to that point. And so we need to be able to come up with interfaces between that microcontroller and that sensor, that microcontroller and that actuator. And those interfaces are often going to be electronic systems. There is also some signal processing that is better to be done in the electronics instead of in the software. There are reasons to do it in terms of the electronics. So there's all sorts of good reasons to do it. I suppose you could also think about the microcontroller being an electronic system on its own. We're not really going to get into that part in this course because we're going to treat it as a computer that magically works and not worry about the electronics that make it work. So we're thinking about the electronics that go around it, basically. Okay, so that's kind of why we're doing this in terms of my perspective, and I'm sure you can add to it in terms of your own perspective. So we're going to think about the building blocks of our electronic systems, and we're going to start with passive building blocks, and then we'll move to active building blocks. So let's start with passive. So we can define things in terms of active and passive. Passive components are those that are not going to require an external power supply. These things just are the way they are. Things like resistors, capacitors, inductors, they do not require an external power supply to provide their properties, right? But an active component is something that does require an external power supply. So a diode, a transistor, various ICs, these all require a power supply in order to do their thing. And so when we think about those two, active versus passive, we are drawing sort of a line in the sand in this case. Now, if you talk to an electrical engineer, they may have a slightly different definition on these things, but this will work for our class. So we're going to start with the passive components, the resistors, the capacitors, the inductors, and then we'll move to the active components. So let's start with resistors. You've seen resistors, you have played with resistors. Resistors are a way of dissipating energy. So they dissipate energy as heat. There are all sorts of different styles of resistors. So in the upper right there, you see a picture of a surface mount resistor. And in the lower left, you see through-hole resistors. We are going to tend to use through-hole resistors simply because they're easier to work with in the lab environment. If you were making a commercial product, you would undoubtedly use surface mount. Either way, whichever style you're doing, there are different power ratings, and you have to make sure that you've got the right power rating, otherwise you're going to get a resistor that will melt, and then it doesn't function properly. So most of the stuff that I've got in the lab is going to be quarter watt. If you buy a kit, it may very well be 1/8 watt. And then when we're dealing with components that need to, things like large capacitors, and we want to dissipate the energy, and then we may need a much larger resistor, or if we're dealing with simply larger power systems, we might need a much larger resistor. I do not have any 1 or 2 watt resistors in the lab. Those are relatively large physically. And I tend to think of those as also being lower resistance values. If you need something that big, be careful, don't use something smaller. You can always calculate your anticipated power dissipation, and if you know your anticipated power dissipation, it helps you choose the right components. When you are choosing your resistor, certainly you're going to go by your resistance value. You should see a color-coded band on the resistors that tells you what the resistance is, or at least the nominal resistance. So a lot of the stuff that we've got is going to be 3 bands worth of value and then 1 band worth of tolerance. And so you've seen these before. You're going to read the bands and you're going to identify the numbers, and then you're going to put those together as first digit, second digit multiplied by the multiplier, and then plus or minus some tolerance. I like to buy the plus or minus 1% tolerance bands. The more precise ones after that, the 0.5, the 0.1, the 0.25, which I don't know why those are out of order. That's odd. I should fix that. Those tend to be much more expensive. And so in terms of ordering stuff for the lab, I usually find that 1% is a nice break point in terms of providing good value for lower cost. You will sometimes see things that have 4 bands instead. Same idea. So why do we use resistors? So here's 2 example circuits that we might deal with in class. On the left, we have a resistor followed by a light emitting diode, an LED. And on the right, we have 2 resistors, and both of these are supplied with 5 volts, which, we do a lot of stuff in terms of TTL, so 5 volts is not unusual. And they're both going to ground. So why might we use these 2 circuits, and why would we choose the resistors, and how would we choose the R values? Well, 2 cases that we deal with a lot. We're going to be limiting current, and we're going to be sometimes dividing voltages. So on the left here, you can see that we have a resistor and an LED. And one of the things about an LED is that most of our red LEDs, and I just use red because that's the one that I always remember, is about 2 volts across the LED. So we would expect a voltage drop of about 2 volts. And so that resistor is going to take up the remaining about 3 volts. And by choosing the resistance value, we can control how much current goes through the LED. If we choose a resistance value that's too low, we could very well end up putting too much current through the LED. And if we put too much current through the LED, it might very well fail. If we put too little current through the LED, then it might not light up bright enough that we can see it. So way back when I was in grad school, I was working with another student, and that student was using some enormous LEDs to indicate something to a human that was part of our test. So there was a red one and a green one to tell him when to start and stop the test. And the student was having trouble figuring out why the LEDs were not turning on. It turns out that student had provided too little current, and they were turning on, they just weren't turning on brightly. And so one of those things that we always want to check is, are we limiting the current correctly? Is there too much? Is there too little? There's always going to be a spec sheet for your LED that's going to tell you what the power dissipation, maximum power dissipation is. So that'll give you an upper bound, and lower bound is going to be based on visibility. In terms of voltage divider, well, we might use something like this in order to set the voltage in the middle here. And so if we know what the R values are, then we can figure out what that middle voltage is going to be. We will use this in an A to D conversion. We'll make a flash ADC like that. All right, so resistors, those are fun. Capacitors, you've seen these before. These are going to store energy in an electric field. They're going to be rated in terms of microfarads or picofarads. You might see them rated in terms of nanofarads. You might even get some really big ones that are in terms of farads, but most of the things that we're going to deal with are going to be in microfarads. You can get them in 2 styles. You can get non-polarized and polarized. Your non-polarized look like this. They do not have any sort of marking to tell you a plus or minus side over here. You can see that the leads are not clearly marked in terms of one side or the other. They work either way. Versus your polarized ones, and now you can see that there are these definite marks. And so right here in this band, you've got 2 marks, and those 2 marks are negative signs. Those tell you on the negative side, and then the other one is the positive side. And if you reverse them, bad things happen. Again, thinking back to grad school, I remember I had a particular circuit board laid out, and I don't remember if I did it or if somebody else did it, but there was a capacitor in there that was reversed. And so when we applied a fairly high voltage, it exploded. Now, fortunately, it didn't explode and cause too much of a problem. There was the little filler stuff went everywhere. So always want to make sure that you don't reverse these. Otherwise, you could see them popping, which would not usually be a good thing. These do tend to have a shorter life. You will see that on the ends here, not visible in these pictures, there will often be some sort of arrangement like this with some marks, and that allows these things to clearly fail when the fluid, sorry, fluid is not the right word. When the dielectric in there is getting older, it'll tend to expand a little bit, and you'll see a little bit of a bulge, and that bulge tells you that the capacitor is no longer good. So in electronics, if you start to say, hear a hum in your speakers, sometimes it's because your driving circuit has a bad capacitor and you could replace it. But be careful with these because they can hold a significant amount of energy, and so that's a good reason to have a large resistor hanging around to dissipate the energy before removing them. If you dissipate it through your fingers, it's going to hurt, so don't touch them unless they are absolutely dead. The big ones, they hold a lot. Things that we might do with capacitors, well, here's a good example. If you like air conditioning, then the unit outside has a large capacitor on it, and if that capacitor fails, then your air conditioning fails. Now, when your air conditioning fails, you can usually get it to go again if you use a broom handle or something to give it a little kickstart, a mechanical kickstart on the fan. What your capacitor is doing is providing an electric kickstart, and you'll see that in other applications as well, where it needs a little bit of burst current in order to get going. So your fan, for instance, needs to overcome that static friction, the stiction, and so it needs a little extra current, and the capacitor will provide that. Yeah. So that's energy storage. We might also have fun things like filters, where we have a resistor and a capacitor applied to some input, and then we can measure the output and it smooths it out. That's a low pass filter. That's a first order low pass filter. There are certainly other examples. Let's see, we've got inductors. We're also storing energy. This is in a magnetic field this time. We have things in terms of microhenries. So we will also see filters, same as we see RC filters. We could have LC filters. We can have RLC filters. We can have all sorts of different analog filters. You'll also see them in terms of mechanical switches a lot of times. Here's an example right here. We've got a lovely switch that you energize one part of it in order to flip the switch. You can see, well, when you think about relays, there are mechanical relays, and there's also solid state relays that don't have that mechanical element. But the mechanical relays, they allow you to separate the high power and the low power very nicely. They also do fail mechanically, so they don't last forever, but they're very nice for separating high and low power. So when we're thinking about analysis of passive components, we usually start with current. And so the idea of current originates from Ben Franklin, I suppose, before that. But Ben Franklin is the one that gives us this idea of conventional current flow. So he visualized this as an invisible fluid moving from one side to the other. And so we think of that as being our conventional current flow, moving from positive to negative. Now, we know that he's wrong, that it's actually the movement of electrons, and the electrons are moving from the negatively charged to the positively charged. So when we talk about conventional current flow, it's going opposite of the electrons. We will stick for our analysis with the conventional flow and not the electron flow, but just be aware that there is a difference between the two. So we've got our Kirchhoff's laws, we've got our Ohm's law, we've got our capacitors, inductors, and so with these things, putting it all together, we should be able to solve any basic circuit problems. And you have done these before in your circuits class. Just quick refresh on all these things. So if we think about Kirchhoff tells us that we've got the sum of the current at a node is just where we've got these junction between wires, is going to be 0. So if in this particular node we have the currents, they are all facing in, and so we do need to have a directionality here. We could do them all facing in, we could do them all facing out. It doesn't matter as long as we're consistent. So if we sum all of them as positive being in, then we'd say that I1, I2, I3 is all going to sum to 0. Looking at this, you say, well, that's silly, of course, because we know they shouldn't all be pointing in. So one of these must be reversed, and so depending on the rest of the circuit, is it I1, I2, I3? You could make an educated guess, but one of these is absolutely going the other direction. So because we can draw a node as any point that connects these things, so with a resistor and hopefully that shows up on your screen correctly, a capacitor in series like this, we can draw in our node, and then we know that we've got IR and IC as being the current through the resistor and the current through the capacitor respectively. And so at that node, we know that the current in has to be equal to the current out, because certainly we would say, just like in the above equation, we'd have IR plus the negative IC is equal to 0. There we go. That's assuming they're both pointing in, and in this case we know IC is pointing out. We can do the same sort of thing with a voltage law. We know that Kirchhoff tells us as we go around the closed circuit, then the sum of the voltage drops is going to be 0. And I do point out this is voltage drops across elements. Sometimes I see students that are confused. It's the drop across the element. So we've got, for instance, a drop across the supply and a drop across the resistor. And so if we go from bottom left around, then we go from negative to positive on the source. We go from positive to negative on the resistor. So minus Vs plus Vr is equal to 0. Similarly, as we go around this loop, we're going to go across the resistor and across the capacitor. We'll go across the resistor from negative to positive and across the capacitor from positive to negative, and so we know that VR is going to be equal to VC. And that's something you've already seen before, that elements in a parallel circuit are going to have the same voltage drop. So we got our Kirchhoff's laws. You can do the capacitors, you can do the resistors, you can do the inductors. So that should be everything we need to put these together. I do want to draw a quick distinction here between high and low power. I mentioned relays as separating high and low power. Again, this is one of those definitions that is sort of a way to think of this in terms of this class, but I don't want to tell you that it's any sort of special worldwide definition. So when I think about high and low power, I think of low power as being things that are on the order of tens of milliamps, often 3.3 or 5 volts, because those are our logic supply voltages. High power I think of as being more than 5 volts. I think of it as being more than hundreds of milliamps. So when I think of high power, I'm thinking of actuators. When I'm thinking low power, I'm thinking more of microcontrollers. And then sensors can go in either way, because some sensors are low power and some, like our IR sensors, tend to draw more power, more current. And so I think of them as being high power sensors. There are some of each. So LEDs, indicators, they could go on either side. Most of them that we're going to deal with are going to be low power, but there are certainly some larger ones that are going to draw more current, and we might think of them as high power. And so, yeah, just bear that in mind. So when I'm thinking about an RC circuit, I am going to apply an input that is on the left there as being some sort of source voltage. I've got a resistor, I've got a capacitor. My output is going to be the voltage drop across the capacitor. So I've labeled my components, including a current. Notice there's only one current flowing through the entire thing, so I've just labeled it as I. We have KVL we can apply right away. So as I go around the loop, I'm going to start at the bottom left. I'm going to go around. And so I've got minus Vs plus Vr plus Vc is all going to be equal to 0. That's KVL, sorry. And so I might rearrange that and say, well, the drop across the resistor is the source voltage minus the capacitor voltage. And it's not explicit in this case, but these are certainly functions of time. These are all three functions of time. So if I apply Ohm's law, well, I can look at that resistor, and so I can say, well, the voltage drop across the resistor, VR, I've already determined that that's Vs minus Vc, divided by R is going to be equal to the current through the resistor, I sub R. But I sub R is the same as the current through the capacitor, because again, I can put in a node right here and figure the current through each side of the node is the same. And so what is the current through my capacitor? Well, it is C times the derivative dVc dt, because again, the voltages are time varying. In fact, the currents are time varying too. So with that, now I can start combining things. So I'll get rid of my currents, they're no longer necessary. So now I've got Vs minus Vc over R is going to be equal to C times dVc dt. And so I'll put the Vc on the same side as the dVc dt. And alternatively, I could write it like this in terms of dVc dt. But more likely for my purposes, I'm going to do it like this, with a Vc dot and a Vc and a Vs. And so this is the form we might use for our undergraduate level controls courses, where we might go to a Laplace transform and a transfer function. But for now, we're just going to say good enough. We're going to stop there. So that is a real quick example of passive components and passive component analysis. So we're going to stop this video and we will pick up with part 2, which is going to be our active components. So moving on.